Hello. Now that we've gone through basic probability, I feel better about going through this topic. But in reality, if you're still weak with probability, or if you're new to the whole theory, then one video is not going to do much. So you may still find this one hard. But the good news is you probably won't have to do much of this, or at least you'll only be doing the very basics. In fact, the analysis that we're going to be doing here is probably too hard for me to ask you in the exam, assuming you haven't seen it before. The one that we have here, you're going to see me doing like an average case analysis of an algorithm, and well, you see how it can be done in this case, so I assume that you can repeat it if I ask you a question in the exam. But yeah, you don't have to worry about me asking something completely new on this topic, on topic of probability. It'll be something that we discuss in this lecture. Okay, so I think it's going to be hard if you're weak with probability, but I'll try not to make it a hard question, if you know what I mean. So yeah, anyway, let's get started. So probabilistic analysis, what is it? This is when you use probability to analyze the running time of an algorithm. I should probably say the average case running time of an algorithm. You see how we focus on best case? Well, actually, we never talk about best case, so because who cares about best case, right? But before, we only talk about worst case running time of an algorithm. And I can mention at the start that average case is kind of hard to derive, and this will show you some of that. And this is going to be the main example in our discussion. It's a very simple code. It's basically you finding the largest element in the array. So spend a second trying to read that code and make sure you understand how it works. Right? You're just going to look at every single element in the array, and if it's bigger, then you're going to assign that to max. So if we look at this code, there are only two main operations here. One is comparison, that's on line 4, and one is assignment on line 5. So I can write the code like this. We're going to set m to be the first element, and then we're going to replace m with something else if that something else is bigger than m. Okay? Right, so, and because we only have two operations, let's just say that the assignment costs CA and the comparison costs CC. Okay, so what is the running time of this algorithm? Well, you have to compare all elements, right? So that will cost you CC times n. But for assignments, do you have to do n assignments? We may have to do an assignment, but you expect that, well, sometimes we only have to do one assignment operation. What if the first element is actually the largest one, right? You'll be doing a lot of comparisons, but you will never actually modify m because m is already the largest element, right? But in the worst case scenario, you may have to do one assignment after each comparison. So can you think about the our worst case input? Like, what would that be? That would be an array which is sorted in ascending order. So every time you get to a new element that is larger than the one before it, so you have to modify m. So worst case scenario, complexity just on. Well, if you want to be exact, it's going to be n times cc plus ca here. But it's reasonable to expect that you don't need to do n assignments on average, right? And just to make it simple, let's just ignore CC because you have to do one comparison anyway. Let's just concentrate on CA, which is the cost of assignment. So what do you think is the average number of assignment? And I should say here that the most common guess is 2, which should actually be 2.5 because, right, you have to do at least one assignment. If the first one is the largest, you have to do at least one. And at most, you have to do 4. And people just take the average. Well, the average is going to be 1 plus 4, 1 plus 2 plus 3 plus 4 divided by 4, which is 2.5. So this is the most common answer. And what I'm going to do here is going to show you that, well, in the last video, I told you that probability can be counterintuitive. So the same thing here, you got to be careful when you do stuff with probability. Like now we're going to analyze the average case, we need probability, and they can mess you up. So this is one example. Okay, so to do probabilistic analysis properly, to do the average case analysis properly, you have to know the distribution of your input data. Like, what kind of input are you getting? Because if all your inputs going to be arrays in ascending order, then you will have to do the worst case complexity every time. You have to do n assignments every time. There's no helping it, right? So now what we're doing here is we're assuming that your input is random. And we're going to assume a uniform random permutation. That is, you have many permutations of like arrays coming in. And we're going to say that every single instance has an equal chance of happening. So how many different inputs are possible? If I give you an array of size n, how many permutations can you have? That would be n factorial, right? And we're going to say that each one of those n factorial combinations is equally likely. So again, that is the big assumption that we're doing here. And same question as before, like you have all these permutations, and how many of these you reckon is going to require 2 assignment operations? Or 2.5? Like, what do you think is the average assignment operations it's going to take? So here is all the combinations, or all the permutation, I should say, of an array of size 4. And we're going to assume that all the elements are distinct, just to make it easy. All right? So there are 4 factorial, 24 combinations, all listed there. And my question to you is, how many of them requires 4 assignments? And the answer is just 1. 1, 2, 3, 4. Everything else requires less than 4. I mean, you can check it out. But only ascending order will require 4 assignments, right? That's the worst case. And there's only 1 ascending order in all the permutations. So now, all of these are equally likely to happen. And only 1 is in ascending order. Now, conversely, how many of these permutations you reckon only need 1 assignment operations? So when is it that you only need 1 assignment operation? That is when you look at the first element and it's already the largest, right? So the largest value here is 4, which means all these guys on the on the rightmost column, these 6 events, these 6 permutations, they only require 1 assignment operation. So now let's go back to my question. Like, what do you think is the average number of assignments you need? If you were answering 2 or 2.5, do you still think so? In fact, here's the number of assignments that you need to do. You see 1 4 here, a bunch of 1s, a bunch of 2s, and a bunch of 3s. So the average number of assignments actually, well, if you add them all up, you're going to get 50. And there are 24 cases. So the average number of assignments is 3.082. So that's actually pretty close to 2. But it's not exactly 2. It's not 2.5. It's a bit more complicated than that. But in fact, if you increase n, and I actually ran a program that compute this, this is the average number of assignments. So with 4, you have 2.083, sure. But with 10, you got 2.9. You probably guess it was 5 or somewhere near 5. With 12, it's actually 3, not somewhere near 6. So the average number of assignments that you do, they don't seem linear. Like, it doesn't grow with n, right? Like 8, 9, 10, 11, 12. This is like 2.7, 2.8, 2.9, 3, 3.1. Goes up much slower. In fact, it looks like a log function. This is the number of assignment you have to do seems to be like some constant times log n, because it grows very slowly. And actually it is. And that is what we're going to show now. We're going to show that this is actually the average case complexity of that algorithm is actually big O log n. So how do we do that? Okay, you need to do one assignment if the element that you're looking at is greater than any other element before it. So that's the only time you have to do that assignment, right? It has to be bigger than every other element before it. Okay, so now the elements are arranged randomly. And let's say you have, I don't know, I elements. If you've got I elements, each one of those I elements are equally likely to be the greatest element. So what does it mean? Okay, if you only have one element in the array, then that's got to be the largest one. If you got two elements, then each has 1/2 chance of being the greatest element. So with just two elements, think about the expected number of assignments that you have to do. If the first one is the larger one, then you only need to do one. If the second one is larger, you need to do two, right? Because you assign the first one to m, and then you check the second one is larger, then you modify m. So you gotta do two assignments. So either one or two, 50% chance each. The expected number of assignment is 1/2 times 1 plus 1/2 times 2, which is 1.5 assignments. So hopefully you remember the stuff we did on expected values. Well, this is it. This is you using expected values to work out the number of operations that you have to do. So if you got 3 elements, each element has 1/3 chance, and then so on. Now that's going to be a bit more complicated to analyze. So let's now generalize. So let's say you have, well, I elements still. Let's look at this case. You got x1, x2, x3, x4. You don't know which one's biggest. Okay, when you start with the first one, you have to do one assignment. So the expected number of assignments is at least one. You got to do this one. Now the next one. What is the probability that x2 is the largest element so far, meaning it's larger than x1? Like, you only have 2 elements, so the chance of this being bigger is 1/2. So the number of assignments you have to do is, well, 0 if it's smaller than x1, 50% chance. 1 is bigger than x1, 50% chance. So 0 times 1 plus 1/2 times 1, what is that? 0.5. That is the expected number of assignment that you have to do on the second entry, on the second element. Now let's go to x3. You have to do one assignment when you get to x3 if x3 is bigger than x1 and also bigger than x2. What's the chance of that happening? 1 in 3. Right? Because you only have 3 numbers. You have 3 numbers, so well, any 3 from any one of the 3 can be the largest element. So if x3 is the largest element, the chance of that happening is 1/3. What about the number of assignments? Well, you have to do an assignment only when x3 is bigger than both x1 and x2. You have to do one assignment. If x3 is smaller than x1 or smaller than x2, doesn't matter, then you only have to do 0 assignments. Well, so again, the expected number of assignment is 2/3 times 0, as in x3 is smaller than x1, x2, plus 1/3 times 1. So it's just 1 times 1/3. And repeat the same process, the same thing for x4. The chance of that being bigger than the other 3 is 1/4. So the number of assignment that you expect to do is just 1/4, 0.25. So that is the expected number of assignments. And this is what we call a harmonic series. Now, you don't need to know the formula If you do need it for the exam, I'll put it on the question, so you don't need to memorize this. But yeah, you see how this is exactly the number of operations, or well, assignment operation that we have to do, which is 1 over I for I1 up to n, and this is log n. Like they sum up to log n plus 1. Actually, this is the definition of log. Okay, so the average gate complexity of the algorithm is actually big O log n. Well, in terms of number of assignments, like comparison is still O(n), but in terms of assignment operations is big O log n, which is better than the worst case of O(n), right? So that is an example of average case complexity. Or actually, I should say the example of us doing an average case complexity analysis on an algorithm. And as you can see, it's not that straightforward. You have to understand a bit about probability, about expected values. And also, some of you probably thought that, well, it seems like the average case complexity is like n over 2. Because you might be influenced by the average case complexity of a linear search, where you're only looking for an element in an array. Like if you're looking for something in an array size n, you expect to get it around halfway point. Like over a long term, you expect to find it after like you look at half the elements inside the array. And in that case, the complexity is n over 2. Which is still big O of n. The same with the worst case complexity. But if you look at how we derive that using probability, it's actually different to the harmonic series we have here. So this is 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over dot 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 plus 1 over n. In the case of linear search, it's not that. And here the operation is just the comparison operation, because you just compare, and if it's the same one, you finish, right? So every element has 1 for n chance of being the element you're looking for. If the first element is the element you're looking for, then you only have to do one operation, one comparison operation, and you're done. The chance of that happening is 1 times 1 for n, right? Because there's 1 over n chance of it being the element you're looking for. You have to do one operation. Expected number operation, 1 over n. If the first element is not it, then if the second element is the one you're looking for, then you have to do 2 comparison operations. So again, the expected number operation is 2 over n. And so on. So you have 1 over n plus 2 over n plus 3 over n plus dot plus n over n when you get the last one. Well, it should be there. So this kind of gives you the 1. It tells you that you have to do at least one operation here. So that's the this is the formula, 1 over n times sum from I equal to 1 up to n, which is just the, well, you've seen this, right? The sum that you always see, and you know this is O(n) squared. Well, but you divide it by n, so the average case complexity of linear search is big O of n, which I hope is what you have in mind anyway when you think about the average number of operations you have to do when you're doing linear search. So you probably have never done this kind of like math to derive it. You probably just think about this in terms of like intuition. You only have an intuition that it's roughly n over 2, but it is, as you can see here. And this is a very common form that you see when you try to derive the the average case complexity of linear algorithms. But make sure you understand the difference between this one, harmonic series, and this just actually I don't know what to call this. It's just the summation, right? Yeah, these are 2 different cases that you often see when you're analyzing average case complexity. And guess what? that's pretty much it. So all this video is doing is showing you an example of doing a average case complexity analysis, which I claim is not trivial. Well, the example that you saw there, they're easy, because they are very, very simple algorithms. But if you want to know more, you can just go look at CLRS. Just look up the index average case analysis. Go to that page, and you'll see how complicated it gets. They have one on the average case of average case complexity of quicksort, and that's pretty hard. We'll talk about that in the next lecture as well. Quicksort. So again, finding the average case complexity is hard because you have to understand probability and you have to understand statistics. You have to, well, you assume the distribution of the input data, and right now we're just assuming it's uniform, but that's not always the case. You have geometric distribution, you have Poisson distribution, you have I don't know, gamma distribution. So there's a lot of distribution that you can get. So understand that we are doing something very simple, and if you ever need to do this in real life, you have to pick up a lot more on probability theory. Okay, so yeah, I think the stuff that we're going to be doing this unit, you should already have a good intuition on it anyway, because like I said, mostly going to be concerned with an array where you can pick every element. Well, the chance of the value you're finding is in one of the entry is just 1 over n, like it's uniform. So hopefully that won't make it too hard. Okay, so that is it on probabilistic analysis. And next one, we're going to do randomized algorithm, which is a slightly different concept. All right, I'll see you then.